Moosmüller. Carolyn is a visiting assistant professor in the Department of Mathematics at UCSD, so we've been very lucky to have her for the last couple of years. She received the PhD from Graz University of Technology in Austria in 2017, and before she joined UCSD, she was a postdoc at Johns Hopkins until 2019. Carolyn's research is broad. She focuses on the development of numerical methods for nonlinear and high-dimensional data. She works on optimal transport problems in machine learning, and she's interested in applications to biology and to cancer research. And today she's going to tell us about distribution classification via optimal transport. So it's all yours, Carolyn.
Okay, sounds great. Thank you so much for the introduction and for inviting me. The talk is about efficient distribution classification via optimal transport embeddings. And really what I want to talk about is how can we efficiently classify and compare distributions while at the same time using the optimal transport framework. So this is the main idea. I want to mention that this talk is based on joint work with a couple of people from UCSD. So one of them being Alex Cloninger, who is a professor at UCSD, and then for the graduate students, Harish, Varun, and Ginji, who did a lot of research in the past months that I will be presenting. And I also want to acknowledge funding from the NSF. So this is my introductory slide. What is the overview of the talk? I will have mainly 5 parts in this talk, while the last one is just a summary. So really, we're going to focus on the first 4. I will give a motivational introduction to what I mean by learning on distributions, and then talk about the optimal transport theory and embedding and how we're going to use that to do this learning problem on distributions. The third part will be about theoretical results, so things that we were able to prove in this setup. And then the last one about some experiments we ran mostly on image classification tasks. Okay, so that's the overview, that's the outline. I will start with the learning on distributions problem and what I mean by that, and what mainly the 2 topics of this talk will be about. So the 2 topics will be most focused on unsupervised learning and then supervised learning. Okay, so what problem am I talking about? I'm talking about data points that come in the form of distributions. So not really the usual setup that we know about where you have a vector in a linear space and you try to say something about that, but really each instance of distribution itself, or a histogram, or if you do applications, point sample from the distribution. And potential application areas or examples of such data sets could be images, which can be thought of as distribution over pixel grid, or for example, gene expression data, which can be considered as a distribution over a gene network. And then when we have this kind of data sets, a question that we're interested in, or could be interested in, is about trying to compare different distributions. So is the distribution of the gene expression data of one patient similar to the distribution gene expression data of another patient, while one patient has cancer and the other does not have cancer? Is there any difference between those distributions? Can we say something about specific cancer types based on these distributions? Or, in image classification, a very basic problem would be, is it a 7 or is it an 8, right? So I think the general setup here, the general question is, we're trying to compare distributions or infer relations between distributions. And so, so the first question I pose has to do with, given a couple of distributions, mu I up to mu n, can we find all pairwise distances? And most importantly, can we do it in an efficient way? So you're given n patients and you want to compare all of them, trying to figure out, are they similar, are they different? And doing all pairwise distances, meaning doing n choose 2 distances. So if one distance is expensive, which can happen with statistical distances, right? Then doing n choose 2 can be a very computationally expensive problem. So one of the questions here somehow is, how can we do this kind of unsupervised learning clustering problem based on distances in an efficient way? And I will talk a lot about optimal transport. So the distance we're looking for here will actually be the Wasserstein distance. But of course, there are other distances that you could consider. Okay, so this is the first question, the first main question. The second question will be about supervised learning. So here, given our data, and we already, I mean, data meaning the distributions or histograms, we already have a couple of labels for some of them, right? So for a couple of images, you already know, okay, image 4 has a label 4, or this patient has the label, if you do it in a very simple setting, has the label cancer. And we use that information to build a function that maps the distribution to its correct label. And then if new data comes in, right? So if we have new training, we have new testing data. So a new patient comes in, we can use that function to map the patient, hopefully to the correct label, trying to figure out, does this gene expression data mean cancer or does it mean healthy? This would be one of the applications. Or in the image classification, is the following image a 4 or a 7? Okay, so these are the two main questions I will be talking about. So doing learning questions on data sets where each instance of data is a distribution. And I'm going to assume a couple of things in order to do that. So, the set of distributions or the set of probability measures, if more mathematically, is a nonlinear space. It's an infinite dimensional space. It can be pretty complicated to do things in there. And usually when we do learning, we like to do it in at least a Hilbert space. What I want to do is somehow try to move that problem into a different setting, into a linear setting. So we're going to use some kind of embedding idea. So assumptions and goals, we're going to address those two questions by embedding the space of nonlinear distributions into an L2 space using the optimal transport framework. So here the optimal transport is going to come in. And then once we're in the linear space, we're going to use linear distance as a linear classifier. And then obviously the question is, how well does that work? Under which setups does it work? And in general, is this a good idea or not? So this is somehow what we're going to do. So we're not going to do it in the nonlinear space. We're actually going to move the whole problem to a different space, which is a common theme, right? So doing embeddings, trying to move into a simpler space. It's, people like to do that. Okay, so assumptions that we're going to do this problem are mainly of the following type. We're going to consider distributions that have been created by a process based on something which we will term elementary transformations. So we're not going to consider all kind of complicated types of distributions, but we're going to say, okay, for example, we want to say something about images of brains and a brain tumor, right? So you have one image of a brain with a brain tumor, and then there's another image with a different tumor. And to get from one tumor to the other, there might be a simple function to do that, right? Like a shift. So for some kind of applications, the underlying function space might actually be simple. And this is the kind of assumption we are doing. So the way that the distribution have been created was by some kind of elementary transformations like shifts or scalings and specific type of shearings, which I will talk about later as well. So this will be the assumption. Each instance of our data has been created by a generation process using simple functions. And then we're going to see, and this is one of the reasons we're doing this simplification, that the computation scales with the complexity of H. So if H is a simple space, computation will be simpler. And then the goal for our feature space, mostly about, doing the unsupervised learning. So meaning we're going into the feature space and then approximating the Wasserstein distance, the distance between distributions, which I just denote by D, but it's going to be the Wasserstein distance, with a linear distance, linear L2 distance, or if we do, if we discretize, it's going to be a Euclidean distance. The second goal is will have to do with supervised learning, meaning that if we have two sets of distributions, two classes, embed them into the embedding space, and then try to separate them with linear methods. So everything that we want to do is linear. And this should go via this kind of feature space embedding idea using optimal transport. Okay, so this is my introductory part. So this is basically the topics I want to discuss today. The next thing will be about the optimal transport theory and this embedding that I mentioned. And it's just going to be a short introduction in case you have not seen it before. And then I'm going to relate it to these learning problems. But basically, optimal transport is about finding a distance or comparing distributions. So it's definitely very related to what I just talked about. Okay, so what is this about? Optimal transport basically says the following. If you have a distance on your ground space, like you have an R to the n Euclidean distance, then you can lift the distance to a distance on the space of distributions. And so the overall idea is starting from the ground space, we lift it to a distance on the space of distributions, which are supported on the ground space. And it was originally posed by Monge, who basically described it in a more applicable setting, saying you have this pile of sand, mu, and you want to move it into the whole mu, using the least work necessary. So actually, if you have to move the sand from mu into nu, what is the work that you need to do? Well, it's the amount of sand that you have to move times the distance that you have to carry it, right? And this is basically the idea of optimal transport. Moving sand into a hole using the least work necessary. And this has a mathematical description as well. This is the next thing I want to show you. So I'm going to talk about the Wasserstein-2 distance, which is a particular type of distance. There are others as well, right? Instead of 2, you can use p. And I'm going to talk about it in where the ground space is r to the n. So you're going to use Euclidean distance on the ground space, but you can think about manifolds as well, and then Riemannian distance, for example. Okay, so what is the mathematical formulation? Basically what I just said. You want to find a map. So in this case, I'm going to talk about optimal transport in the mapping setting. A map that moves the pile of sand mu into the whole mu. So we usually write this with this push forward notation, T push mu equals mu, while at the same time minimizing the overall work. So work is given by the distance I have to travel, T of x minus x, times the infinitesimal amount of sand I have to move, and then integrate over the entire space. And we want to find a function that minimizes this work. And this function is going to be called the optimal transport map from mu to nu. And the minimum, so the cost that we need in order to do that, is called the Wasserstein distance, and denoted by W to mu nu. And I also have a plot of a discrete setup, so one can also formulate the whole thing in the discrete setting, where you're not really about smooth distributions, but about discrete distributions. And then the map is basically trying to do an optimal matching in some sense. So this is one formulation of optimal transport. It's a specific kind of formulation. So we can make this more general, and usually this is what people prefer to do. Instead of talking about a function, and we talk about couplings, where we allow to separate mass. So it's not like one point has to be mapped to another point, but we allow that a point spreads the mass to different points. But today I will stick to this function setting. Okay, so we got a map, T mu nu. It exists and is unique if you have certain assumptions on mu and nu. And we got a distance between distributions, right? So this is somehow related already to the unsupervised learning problem I talked about in the beginning. So this is a distance, right? We can use it to put things together which are similar to cluster things if we want. We have not really talked about the supervised setting at this point, but at least we know something about the unsupervised setting. So what are properties of optimal transport? First of all, I mentioned this before, the theory is very well developed. Many people have worked on this and still work on it. It's a metric on this probability space, which is useful. It's a distance. We can do interpolation between distributions in a very nice way. And it incorporates the geometry of the underlying space, right? In the thing I showed before, it's the Euclidean distance, but you can use different distances in different spaces. Now we're coming to the computational side. So trying to find this optimal transport map can be slow. And if you set it up in a discrete setting, it's basically a linear program, which can, if the sizes of the distribution is large, can be problematic. There are ways to make this faster. So this is the famous paper by Couturi about adding a regularizer and using a synchron scaling algorithm. But still, if we want to do a lot of pairwise distances, right? So if you want to compare a lot of images, you have many patients, and choose two optimal transport computations might still be a little bit too expensive. So, yeah, and also the complexity, it can be independent of the family of distribution. So if your family of distribution is very simple, it might not be reflected in this setup. So how can we do learning in this setting? Well, I mentioned already, this is a distance, right? You can use it for unsupervised learning, that's good. We don't have a feature space at this point. So it's not immediately clear how we could do learning using that optimal transport setup. And this is what I want to talk about next. So this embedding idea, this feature space idea, and how we can use optimal transport to do that. And then, then we will see in like theoretical results and experiments when this works and what the restrictions are somehow. Okay, so let's talk a little bit about this embedding thing. It's called linear optimal transport. So basically, it's a linearization idea. It's an idea of moving a manifold to a tangent space, basically. And then once in a tangent space, you can do linear methods if you want. So it's called linear optimal transport, for short LOT. I want to start by mentioning that this is not my idea or the idea of my co-authors, but it has been studied by other people before and is still being studied by other people. So this is an interesting field. I have a few citations on my slide, and it dates back to 2013, where Gustavo Rode first suggested this kind of idea. And since then, many people have worked on the theory, the algorithm, and shown some interesting classification results. Anyways, so we also work on that. I just want to introduce what the embedding is. So what we're saying here is we are using the transport map as a feature of a distribution. So we're picking a reference, call it sigma. It's something you choose, right? So it can be a Gaussian, can be a Lebesgue measure, can be anything else, can be part of your data set. And then you map any other distribution, mu, to the optimal transport map that takes sigma to mu. So what we're saying is you start with a distribution, right? It could be gene expression data from a patient, and you identify it in some sense with the optimal transport map that takes sigma to mu, and sigma is being fixed. With the idea being that if you have two different mu's and you map them to the same reference, the map should be different as well, right? While if the mu's are similar and you map it to the same thing, the map should be similar as well. So somehow this should, reflect some of the properties of mu. It should be a feature of mu. So this is the idea. This is the main idea. And it takes us to a linear space or to a Hilbert space. It takes us to L2. So from the nonlinear space, it takes us into L2. And once we are in L2, we have all of the things like the algorithms that exist for linear spaces. Okay, so this is something you can do, and it's defined. The question is, why do we care? Okay, so, well, they're again related to the two questions I posed. It's about distances and it's about supervised learning. So on the distance side, we can define a linear distance. And we call it already W2-LOT to give you an impression that we want to connect it to the original W2 distance. And so what is it? You have two distributions, you map it into the embedding space, and you take the L2 distance weighted by the reference. That's the distance, you can define that. Obviously the question is it an approximation of the Wasserstein distance? We will see some settings in which this is the case. And the other thing is about supervised learning. So instead of trying to learn a function that takes a distribution to its class, image of a 7 to label 7, we first embed the image into the linear space and then learn a linear classifier for this label. So this is the whole idea, moving everything into the linear space, using linear methods, and then trying to prove or see, or both, that this actually works. And the obvious questions which are related to that is, first of all, for which distribution does this work? Right? It's from a theoretical point of view, it does not have to work always, right? The one space is non-linear, the other space is linear. They cannot be the same. So there has to be some restrictions. What are the settings under which we can approximate the linear distance with the non-linear distance by the linear distance? And what are the assumptions that we need to actually learn the original classifier, or a function that goes from the non-linear space to the linear space? So what assumptions do we need? So these are the questions I want to discuss. But this is the setup. This is the embedding setup based on optimal transport. Okay, so coming to the questions, for which distributions? And this is what I mentioned at the beginning. We're going to consider sets of distributions that have been created by elementary transformations. So something like a shift, something like a scaling, something like a specific kind of shearing, which I will talk about later. And so really what we're saying is, okay, you have a template image, you have a 1, and you shift it around, you scale it around, you do some shearings, and then you have another class that is which images of 2s have been created by similar kind of things. These kind of setup really work really well in this LOT embedding idea. And the reason is, or the main proof reason somehow, has to do with the fact that they satisfy a property which we term the compatibility condition. So this is the equation in the third item, saying that these functions are already optimal in some sense. Meaning, if you have a distribution, a Gaussian, and you shift it, it's another Gaussian, right? And you compute the optimal transport between the two of them, it's basically a shift. And this is true for scalings as well, and it can be true for certain kinds of shearings. So this property basically tells us, oh, well, the original function already has some nice properties. And this kind of setup works well in the LOT embedding. And well, I have another slide on this property, this compatibility condition, that has to do with a commutative diagram, basically. So these kind of functions interact nicely with the optimal transport setup. What the diagram says is the following. You start with sigma, which is your original reference distribution. And you have something else, the mu, which is the one thing you want to find something out about. You can compute the optimal transport between the two of them. That's the embedding. But then you can shift mu. You can push mu by a shift. You will get a new distribution. And you can compute the optimal transport between the original reference and the new shifted distribution. Is this optimal transport just the original optimal transport plus the shift? This is the question. If this is the case, and it is the case for shifts and scalings, then we are good to go with this distance approximation and with the supervised learning. And if not, we don't have a theory for it. So that's basically the setup. It's a commutative diagram relating, showing the interaction between optimal transport and push forward. This is what it is. Okay, I have one more slide on this, and then we'll continue with something else. So it's basically the question of push forward and LOT being inverse to each other. So if you first do the LOT and then push with the LOT map, with the optimal transport map, you will get back to the original distribution. While if you start with a function, first push a fixed distribution, and then do the LOT embedding, do we get back to the original function or not? And it's the case for shifts and scalings, for certain shearings, but in general, it's not the case. So it's somehow like invertibility of the exponential map kind of problem. So the push forward is the exponential map. LOT is the inverse. Is it always the inverse? Not in general. And something else we study, it's not just about this condition being satisfied exactly, but it also is about, so this is the condition, and it's the other thing that we're interested in has to do with this condition being satisfied up to an error, which usually is the case when you have some kind of application. You will never have a perfect shift or a perfect scaling, but you might have the shift of the tumor, as I talked about before, plus some kind of perturbation, some kind of error. So instead of the theory we develop will always come with this almost compatibility condition. So are we satisfying this property up to an error? And if yes, we can still say something. Of course, there will be an error based on epsilon. But I think it's the more interesting kind of problem, because we're never going to satisfy these kind of things exactly. If we do discretization, if we do numerical algorithms, or if we have data that comes from applications. So really what we're allowing is elementary transformations plus perturbations. Okay, so that's that. Let's talk about the theoretical results. So you know about the original two questions I posed, unsupervised, supervised learning. We talked about optimal transport and this embedding idea, and how we want to use this embedding idea to answer the first two questions. And now what we have to talk about is under which setting does it work, like from a theoretical point of view. And we have a couple of results. They are, there's definitely room for improvement. So this is also the hope that some people get interested. If this is the case, please let me know. And then afterwards, we'll talk about experiments. Okay, so theoretical results. Let's start with the distance. So what we can say about the distance is the following. You want to compute the Wasserstein distance between two distributions that have been created by these elementary transformations I talked about before. So you start with an image of a 1, you shift it. Take the same image, scale it. What is the Wasserstein distance between the two of them? And what we're saying is either you compute the Wasserstein distance, okay, or you embed it and compute the linear distance, this L2 linear distance, which we term W2 LOT. Okay, and what we can say about it is the error that you're making is basically epsilon to the 1/2. So it's a Hölder regularity in epsilon, where epsilon is the amount of perturbation that is allowed from being a perfect shift or a perfect scaling. So basically saying, if there is no perturbation, the error on the right-hand side is 0. So the Wasserstein distance equals the linear distance. So in this very specific case, where the function space is just the elementary transformations without any error, these distances are actually the same. While if you have an error, what you should expect is epsilon to the 1/2 times some constants that mainly have to do with the choice of reference, the choice of original template, and their regularity properties of convex supports. And it's this kind of result basically follows from something that has been proved 10 years ago already. So Nicola Gilli already worked on this kind of embedding and on the Hölder regularity properties. You can also get rid of the regularity assumptions by paying with a little bit of a higher bound. These are also results that I cite here. But the real point is the computational improvement. So it's, we're not interested in comparing two things. The distance between two things, there's no point of doing what I just said. But if you have many things, many patients that you want to compare, the improvement in computation is the following. Instead of doing all pairwise distances in the nonlinear space, in the Wasserstein space, which would be anxious to expensive computations, we embed everything into this LOT space using a reference distribution. These are n optimal transport computations, well, from the reference to everything else, n. And then we do anxious to L2 distances in the embedding space. which should be cheaper than doing the Wasserstein distances. So n computational things, and then n choose 2 cheap things. That's the kind of computational improvement that we can get. And we have a certain kind of knowledge about what is happening with the error once we're doing the approximation. So this is the distance result. Okay, talking about, so this is the first thing, question 1. Question 2, supervised learning. So this is about classifying 2 things based on training data, label knowledge, right? So saying you have 2 classes of images, for example, or 2 classes of patient. One class of images, for example, is 1 shifted around, scaled, and so on. The other class is 2s shifted around, scaled. We can use those 2 classes. They should satisfy a couple of assumptions, but we can take them, embed it into this linear embedding space, and then use a linear classifier. So saying the 2 sets are linearly separable under the assumption that the original 2 sets have a minimal distance, so they should not be overlapping, which is a reasonable assumption. And the function, basically the function space should have certain properties like convexity and compactness. Basically meaning we want to use the Hahn-Banach theorem. So the good thing about this result is the minimal distance that we need in order for this linear separability to hold can be given explicitly based on what your choice of reference is, what the 2 templates are to create the classes, and what epsilon is. Especially if epsilon is 0, so if there's no perturbation, delta can be chosen to be 0, meaning the 2 classes should just be disjoint. While if there is some perturbation error, they should be more than disjoint, but the delta can be given explicitly. Also, this is a generalization of a result by Gustavo Roda and his group, where they proved a similar thing, but in 1 dimensions. So this is a generalization to general dimensions plus allowing the perturbation error. And as I said, we're using the Hahn-Banach theorem. The reason it works, again, has to do with this LOT embedding preserving certain structure. So we talked about its property of preserving distance, at least under the assumption of compatibility. But we can also preserve convexity under the assumption of compatibility. So if you're only considering elementary transformations, convexity is preserved through the embedding. And this is a nice property. And we have the same for almost convexity. So if you, instead of the compatibility condition, you have almost compatible, you will get almost convex. So it's a similar kind of result. Okay, and the last theoretical result I want to mention has to do with this shearing part. So this is some newer results, which we're still working on. Anyway, so what we're saying here is, the central theme of the compatibility condition being satisfied that leads to all of the results brings up the question of for what kind of transformation is it satisfied? And basically what we're saying here is that if we know something about the choice of reference plus the distribution mu that we're interested in, we can classify all functions that will satisfy the compatibility condition as long as this optimal transport map from sigma to mu has a specific kind of property, namely being if you diagonalize the Jacobian, the orthonormal basis should, so the matrix P basically in the orthogonalization should be constant. So this is an assumption that we need. But if we know that, we can basically say, okay, all kind of shearings where the diagonalization goes in the same eigendirection will be compatible with, will satisfy this compatibility condition that I talked about before. And it has to do with basically trying to maintain the convexity of functions. So an optimal transport map can always be written as the gradient of a convex function. And using that fact, we can deduce the set of all functions that will be compatible, especially the set of shearings that will be compatible. Okay, so these are a couple of theoretical results I wanted to mention. The fourth part, this is mainly, well, it's mainly the last part actually, is about experiments that we did. So, I showed you these theoretical results about unsupervised, supervised learning, and what can we do in experiments? And so, we started with a regular, base problem that people like to start with, is about classifying MNIST, right? So MNIST being those images with handwritten digits. And we were saying, okay, let's take images of ones and images of twos, embed it into the LOT embedding space and see what happens. And we did not actually use the original MNIST, which is centered around the middle, but then made the problem a little bit harder, applied some shifts and some scalings so that the digits move around a little bit and see, well, it is overall, it's a little bit more complicated problem, and see what happens. And so, well, what you see in the plot is number of training data that we use versus classification error. So for example, in the first experiment, 40 training images per class, and then test on 100 images per class. And the good thing is, well, first of all, the error goes down as we increase the number of training, which is not surprising. But also the LOT, which is the blue curve, performs pretty well, while compared to doing a dimension reduction plus a linear classifier, so PCA, does not do as well, and also comparing to CNNs. And I think the benefit here has to do with the fact that we can use linear classifiers. They are easy to learn. And so there's a benefit when we have a small training regime, right? So here the amount of training data is very small. If you use a lot of training data, then CNNs will do much better. But here really the point is of trying to reduce the amount of training data, which is especially interesting if you have, for example, medical data, something like this, where it can be expensive to get labels. And one can also do an embedding plot. So once you go to the embedding and then reduce the dimension, where you can actually see how the classes behave in the embedding. And as you increase the training data, we get better in separating the two classes. And you can also see the separating hyperplane, basically the linear result. So this is something one can consider just as a visualization, basically. And we also did some experiments with more involved shearing. So the thing I talked about before was shifts and scalings. But you can also do shearings, right? I talked a little bit about which shearings are allowed. And here at the top, you see MNIST images that have been sheared. And these are like severe shearings, right? So they partially go out of the image and very large or very small. And so we did the same thing. Take those two classes, take it into a linear embedding space, do a linear classifier. This is the blue plot. And we can again see that it goes down so the testing error goes down pretty fast. And the number of training data that is necessary is not too large. So we start with 20 here. And again, comparing it to CNNs. Okay, then, so this is like the basic kind of experiments you might want to start out when trying to do supervised classification. We also played around a little bit with active learning. So, since we're in a linear space, we can basically do anything that, any kind of algorithm that is available for linear data. And so we tried an active learning approach, while I think the application might be a little bit more interesting than the MNIST classification. So here we were actually doing this, asking this, what I mentioned before, this tumor question. So you have images of brains, and the question is there tumor or is there no tumor? So it's a binary classification question. And so what we're doing is this active learning approach, where you're given a couple of training data, and you learn a family of linear classifiers. And then based on that family, try to pick new labels that you want to query. So it's an iterative process that queries new label in every step. And so which labels would you query, right? If all separating hyperplanes identify one of these images as a cancer or no cancer, you would not want to query it because all of them have the same opinion, right? But if if they do not agree on an image, this is the one that you want to query, right? So this would be the next label that you're choosing. So basically it's about trying to figure out the images which are on the margin between all of these linear classifiers. And you can see testing error goes down pretty fast when we do this kind of thing. And it's really an application that is more, hopefully more interesting. So really trying to figure out, is there tumor, is there no tumor? Okay, so that's the active learning. And we also did some other experiments I just quickly want to mention. So this is still ongoing work. But again, I mean, the thing that I just mentioned has room for many types of questions that we still need to answer. One of them being, what is a good choice of reference, right? So the sigma is something that you can choose, and it can be anything, right? At this point, it has to have some properties so that the proofs work. But overall, we have not talked about what would be a good choice for reference. So here we just played a little bit around with different references. So the left plot is a Gaussian reference. The middle plot is taking as reference one of the images from MNIST in this case, and then shearing it. And the last plot is taking one of the original MNIST without shearing it. So these are three kinds of references that we are trying. And so this plot also combines another question that we're asking. It's not just about what is the best reference, but also what happens if I use multiple embeddings, right? So up to now, we were doing one embedding based on one reference. But you can do multiple embeddings, choosing multiple references. This will make the overall computational problem larger, right? Because you have more optimal transports to compute. But it can be worth in certain circumstances when you know, for example, that you have a very large set of functions, right? So the two classes have been created by a very rich set of functions, and one embedding might not be good enough to separate those. So if you use two reference distributions or multiple reference distribution, you're creating a higher dimensional embedding space, which means the classification will be easier. So what you see in the plots is a comparison between different references, plus a comparison what happens if I use multiple references. So in the Gaussian example, the blue line is one Gaussian reference, and the orange line is 5 Gaussian references. And in the middle plot, you have sheared MNIST as a reference. What happens if I use 2 of them, or what happens if I use 10 of them? And so what we see in the plots, at least, is that so using more embeddings does give an improvement. It's not clear if there's a huge difference between 6 and 10 in this example, but there seems to be a difference between 1 or 2 and more. And the other thing that we see is that choosing the reference from the data set improves the classification, which we can also see as a theoretical result, because then this compatibility condition becomes simpler. We don't have to involve a new thing, which is called sigma, but we only need to involve a new thing from the original data set. So it's the mu pushed by something. So it's part of the original data set. And also it somehow makes sense, right? If you have 2 classes which you want to classify, one has been created by ones and the other by a 2. I mean, an image of a 1 and the image of a 2, and you use those 2 as a reference, then everything in this class should be similar to this, but different to the other. But everything in this class should be similar to this, but different to the other. So I think this also makes sense from thinking about it this way. Anyway, so this is another kind of research questions we are currently working on, interested in, especially the question, and we have some results on that tells us how many embeddings we should use, right? So if you know your function space is this large, so it's bounded by L, and you want to achieve a certain amount of separation in your classification, right? So you want the 2 sets to be disjoint by delta, right? So you have a separation level and you have a bound on the function. how many embeddings do I need to achieve a classification of that in that sense? What is the minimal amount, right? I mean, one would be the best thing, but if your function space is very large, it might be impossible. Okay, so this is the last experiment and some kind of ideas for future research that we are interested in. And I think this basically ends the experimental section. I just have one more slide on a summary, basically. So, well, I mainly talked about two questions. One has to do with unsupervised learning, the other one with supervised learning. All of this in this framework of LOT, linear optimal transport. I just want to highlight that the benefit comes from using these elementary transformations. Then we can have a computational improvement. It might still be slow to compute these things, and using syncon might be the solution to that. Again, also what might be interesting is not using the smooth theory, but using a discrete theory instead, right? Because this is more related to applications. And then the supervised learning, basically the question is, you know, we have this theory that works for the compatible transformations, but what happens if I go beyond this epsilon? So what is, if I have different kind of transformations I'm interested in which do not satisfy the compatibility, but I'm still interested, like something like a rotation or something. What can we say about that? So there are a couple of questions which are still open. And yeah, so this is my summary slide. Thank you for your attention. I have a couple of references. If you're interested in other references, please let me know. I can send you a list. And yeah, so if any questions, I'd be happy to answer.
So thank you, Carolyn. That was really nice.